Okay, in this chapter, or rather this section, which is the end of chapter 3, we are going to basically put together everything we've learned so far. Okay? And so our first example, we're going to try to do 3 today. We are going to sketch a graph of 3x cubed minus 10x squared plus 4x plus 10. Okay? So let's do this first. It doesn't matter what order we go in, but how about let's do this first. Let's find the y-intercept. Okay. How do we do that? We plug in 0. And what do we get? We get 10. So the y-intercept is 10, which I believe is right there. Okay. X-intercepts for this might be a bit hard. If it was a quadratic, then I would definitely say find the x-intercepts, because all you need to do is use the quadratic formula. But since this is cubic, let's not worry about the x-intercepts. Okay, but let's find the limit. Oops. Let's find the limit of f of x as x goes to infinity. And let's see what that's going to be. So let's let x go to infinity. Okay. What's this part going to do? That's going to go to infinity, right? And so is this. And so is this, correct? Now, notice that here we have a subtraction. So this is like saying infinity minus infinity plus 10. I wouldn't say that it equals that, but it's like saying that, right? Is that going to come out to be a positive infinity or a negative infinity? I mean, this is a little tricky. Right here, we have infinity minus infinity, right? Is that going to be 0? Well, the answer is no, and here's the reason why. This infinity right here is way bigger than this one, because that's coming from x cubed. And this is coming from x squared. And x is getting infinitely big. Now let me show you a neat trick for doing this. We can take our function and let's factor out an x cubed. Wouldn't it look like this then? 3 minus 10 over x plus 4 over x squared plus 10 over x cubed times x cubed. Isn't that correct? Now let x go to infinity, and what's going to happen? This part's going to disappear. This part's going to disappear. This part's going to disappear. This part's going to go to infinity. So what do we end up with? The limit for this part will just be 3. The limit for this part is infinity. So wouldn't the overall limit then be infinity, right? 3 times something getting infinitely big is going to be infinitely big. Okay? Let's move that down so it's not in the way of our, well, I'll tell you what, we'll move the graph. out of the way, but we'll do that later. Okay, let's write down the limit of f of x as x goes to negative infinity. You do it the same way. I will rewrite the polynomial the same way I did before, 3 minus 10 over x plus 4 over x squared plus 10 over x cubed times x cubed. Let x go to infinity. That fraction will disappear. This fraction will disappear. This fraction will disappear. Oh, I said x goes to infinity. I meant negative infinity this time, right? There we go. All right. This one goes to where? Negative infinity. So this part's going to the number 3. This part's going to negative infinity. So what's the limit that we'll get? Negative infinity. Okay. Now let's find the derivative, because we're going to find the critical points next. Okay. So we'll find the derivative. That equals 9x squared minus 20x plus 4. Is there anywhere that that is undefined? No. Is there anywhere that that might equal 0? Yes, possibly. Let's figure that out. Well, you should be able to just use the quadratic formula. That's just basic algebra, so I'll leave that to you. And we find out that f prime of x equals 0 when x is 2/9 and also when x is 9. So that tells you that we're going to have critical points at those places. Okay, let's go ahead and plug in 2/9 and also 9 because I want to plot these points. Okay, so then we do f of 2/9 equals, and this is just arithmetic, just plug the number 2/9 into that and just work it out. Okay, it equals 25/34 over 243. I want to plot that point, and I don't have a good idea in my mind of, what number is that I'm looking at. So let me just tell you that if we put that into a calculator there, we see that that is approximately 10.4. So that gives me a good idea of where to graph that. It's going to be right about here at 2, 10.4. It's not exactly 10.4, but close. Okay, let's plug in 9 into the function and see what we get. Okay, all you need to solve that is the quadratic formula. That's just basic algebra. So I'm going to leave that to you, and this is what we get when we do the quadratic formula. We find out that f prime of x equals 0 when x equals 2/9 and also when x equals 2. Okay, so that means we're going to have critical points at 2 places. I would like to find exactly where those points are, so let's plug those numbers into our function. F of 2/9 equals 2,534 over 234. Now I want to plot this point, so I need an idea of how big that number actually is. When you have fractions and the numbers in the fraction are really big, it's hard for you to have a good picture in your mind of what the actual fraction is. Because when I look at that, I think, oh, that's a huge number, but it's really not. That is about 10.4. So we're going to have one critical point at 2/9, comma, about 10.4. So let's just put that. It's going to be right about there. Did you see that dot show up in the picture up there? Okay, let's plug in 2 and see what is f of 2. F of 2 equals 2. I find that by just plugging 2 into the function. So we're going to have another critical point at 2, 2. Okay, let's label these points here. So we had 0, 10. That was our y-intercept. Okay, we have 2/9, comma, 2534 over 243. That is some kind of critical point. I think I can guess what kind it is, but I'm going to hold off on that. Okay, and we have 2, 2, which is also a critical point. Okay, now let's find f double prime. F double prime of x equals 18x minus 20. Okay, so watch what I'm going to do for this. I'm going to use that to figure out what kind of critical points I have found so far. In other words, I'm going to plug in 2/9 into f double prime, and I'm going to plug in 2 into f double prime. And I don't really care what's the number I get, I just want to find out is it positive or negative. Okay, so if we plug in 2/9, we get negative 16. What's that tell us about this point? The graph is concave down, and so that is a local what? It's a local max, but we'll get to that in a minute. Okay, plug in 2 and we get positive 16. That's positive, which tells us the graph is concave up right here, so that's a local minimum. But again, we'll get to that in a minute. Okay, here's something else I would like to point out. Where does f prime change from positive to negative? It's negative when x is 2/9, and it's positive when x is 2. So somewhere in between it must have changed from negative to positive. Let's figure out where. Where will f double prime equal 0? It equals 0 when 18x is 20, which means x is 10/9, right? That's where the second derivative equals 0. So the second derivative is negative when x is less than 10/9, and the second derivative is positive when x is greater than 10/9. So the concavity changes when x equals 10/9. That's called a point of inflection. When the concavity changes. Okay, let's plug in 10/9 into our original function up there highlighted in green. Plug in 10/9 and let's see what we get. Okay, when I plug 10/9 into the function, we get 1510 over 243, which, to give you an idea of how big that number is, it's not that big. That is approximately 6.2. So there's a point of inflection at 10/9, comma, 1510 over 243. That's a point of inflection. That's where the concavity changes. So where are we going to graph that? 10/9 is just a tiny bit bigger than 1, and 1510 over 243 is just a little bit bigger than 6. So that point of inflection will be right about here. Right about there. That's our point of inflection. Okay. What else can I do with you? Oh, so let's go ahead and write down the max and min that we had found. We found a relative maximum, and we found a relative minimum. And I'll review with you how we knew that. There's a relative maximum at 2/9, 2534 over 243. There's a relative minimum at 2/2. Let's review how we found those. We took the first derivative and set it equal to 0, and we found these two values. So we know that the function levels out there. We plugged each of those x values into the function to find the corresponding y value. And that's how we came up with those 2 points. But at that point, all we knew was that the function leveled out there because the derivative is 0. How do we know that one's a maximum and the other's a minimum? That's over here. We plug 2/9 into the second derivative and we got a negative number, which means the graph is concave down. So the graph levels out there and it's concave down. And so that means that the graph looks like this, which means that point is a relative maximum. For the other one, we plugged in the number 2 into the second derivative and we got 16, which is positive, so the graph's concave up. So we have the graph leveling out at that point, and it's concave up, so that's how I know that's a relative minimum. Okay, this example comes right out of the book, so it's all explained in writing. If you don't think I'm doing a good job of explaining it, you can see how it is in the book, okay? You should really be looking at the book as you're watching the video. And one more thing I want to do is let's write down what we found out about concavity we found out that the second derivative equals 0 when x is 10/9. And I found out that the second derivative is negative when x is less than 10/9. All you have to do is take a number smaller than 10/9 and plug it into the second derivative, and you'll find out that it's negative. So that means the graph is concave down on the interval from -infinity up to 10/9. Okay, what else did we find out? We found out when you plug in a number bigger than, oh, I said 10/9. Yeah, that's right, 10/9. When you plug in a number bigger than 10/9, the second derivative will be positive, which means the graph will be concave up. On the interval from 10/9 to infinity. Okay. Now one more thing. Let's figure out increasing and decreasing. This is not going to take much work at all. Okay, that requires the first derivative, which is right there. We know where the first derivative equals 0. It equals 0 when x is 2/9 and again when x is 2. What about between those two numbers? And also, what about outside of those two numbers? Take any number smaller than 2/9 and plug it into f prime. I'll let you do that yourself, okay? Pick a number that you like that's smaller than 2/9 and plug it into f prime and see what you get. And I think what you're going to find is that f prime is positive when x is smaller than 2/9. Which means the graph is increasing on the interval from -infinity to 2/9. Now pick a number between 2/9 and 2. Any number you want between 2/9 and 2. And plug it into f prime. And I bet you're going to come out with a negative answer. So f prime is negative when x is between 2/9 and 2. Which means the graph will be decreasing on the interval from 2/9 to 2. And then finally, pick your favorite number bigger than 2. Plug it into f prime, and you'll see that you get a positive answer. So I'm just going to add that on to right here. F prime is positive when x is less than 2/9 or when x is greater than 2. And how do I tell that? I just pick a number greater than 2 and plug it into f prime. So the function will be increasing again on the interval from 2 to infinity. Okay, so we figured out a lot. We figured out here the y-intercept here. we figured out as x goes to infinity, the function goes to infinity. As x goes to negative infinity, the function goes to negative infinity. We found critical points, a relative maximum and a relative minimum. We found out when is the function going up and when is the function going down. We found out when is it concave up, when is it concave down, and we found a point of inflection. That's a lot. So that's everything we've done for this function. So we've got some of it in the picture already. Let's go ahead and just add the rest. Okay. So there's our y-intercept. There's our relative max, there's our relative min, there's our point of inflection, and now let's incorporate this stuff in. The increasing, decreasing, and the concavity. Okay, so where does the increasing, decreasing switch? It switches here at 2/9, and then it switches again at 2. The function is going up in this area over here. It's going up. And then in the middle, the function is going to be going down. And then on the right-hand side, it's going to be going up again. Okay? That'll be easy to put in there. Now, let's also put in the concavity. The concavity switches right here at the point of inflection. Okay, so let's put in this final picture here. Okay, so we have this graph is increasing and concave down. So it's kind of rounded over. It's going to go through that first point that I made, and then it's going to go through that second point, and that's a relative maximum. And then what happens after that? The graph is still concave down, but now it starts decreasing. So it's going to be curved like this. And then it goes through that point of inflection, and now it's going to start being concave up, still decreasing. So it's going to be curved this way. And then it goes through that minimum, and then it starts increasing again and still concave up. And finally, what else am I going to say? It's going to go off to infinity in that direction and down to negative infinity in that direction. And there's a graph of that function. Okay, that seems like a lot, and it is a lot, but it's a lot because that's a review of almost everything we've learned so far in the first half of the semester. Okay? Now, I think we need to practice more. This is a big deal, and I don't think one example is enough, but I also don't want to overwhelm you. So I'm going to wait until the next lecture, and then we'll do another example.